Thank you very much for the invitation and for the opportunity to speak here. Today, I'm going to talk about distance sets spanned by sets of Hausdorff dimension d over 2 in RD. And this is joint work with Pablo Shmerkin. Let's recall the problem. So E is a Borel subset of RD, and the Hausdorff dimension of E is S. Then the distance set delta E is defined as the Euclidean distance defined by any pair of points in E. Now the question is, how large is the distance set? So Faulkner conjectured in 1985 that if the Hausdorff dimension of E is strictly greater than d over 2, then the Lebesgue measure of the distance set is positive. So the reason for this conjecture can be explained by the following example. So we can consider a collection of delta balls in RD that those delta balls, they are centered at lattice points, well, like kind of rescaled lattice points. And the distance between them is about delta to the S over D. So if we calculate, well, let delta goes to 0, or we can kind of iterate this picture many times, then this lattice example will show that the Lebesgue measure of the distance set is positive if S is greater than d over 2. And then the Lebesgue measure of the distance set is 0 if S is smaller or equal to d over 2. So this is the original conjecture of Faulkner, and where the conjecture we are going to study today is a variant of this one. But before that, I want to report some of the bound we had in recent years. So joint with Goussiot-Savage and O, and also with Dewey-Savage, O, and Zhang, we show that if D is even, then if the Hausdorff dimension of E is greater than d over 2 plus 1/4, then the distance set has positive Lebesgue measure. So this Goussiot-Savage and O, we proved for D equals to 2, and then joined with Dewey-Savage, O, and Zhang, we extend this result to higher even dimensions using some kind of projection argument. And this projection argument will be an ingredient in our results today in higher dimensions. And we will see why this D is even is an assumption later. But the main conjecture we want to focus today is that the following. If the Hausdorff dimension of E is greater or equal, so here we allow equal, than d over 2, then the Hausdorff dimension of the distance set is positive. So conjecture 2 is more challenging than the first one, and we study it not because it's more challenging, but because it also has some connection to other areas of mathematics. So here is an example that's called a train track example. Let's consider E to be a collection of small parallel rectangles inside a big rectangle of width 1 and of length 1 and width delta to the 1/2. And those small rectangles has width delta to the 1/2 and length delta to the 1/2 and width delta. The distance between them is delta to 1/2. So again, delta will goes to 0. And if we look at this set, delta will be very small. And if we look at this set, this E is like a morally one-dimensional set at scale delta. And when we draw the distance set, we will see a collection of those small delta intervals with distance about delta to 1/2 apart, at least near 1. And when those small intervals goes to 0, they become slightly denser, but the main part looks like delta to 1/2 apart. So when we look at this distance set, you kind of like find as if we have found a counterexample to this conjecture. In other words, so E looks like one dimension in at scale delta, but its distance set looks like, say, half dimension at scale delta. But this is not quite a counterexample, as this E is only at scale delta, and to make a real fractal set, we need to let delta goes to 0, and this set does not iterate well. That's the reason behind it. But nevertheless, the train track example is like one of the main obstacles we need to overcome if we try to study sets of Hausdorff dimension d over 2. Are there any questions so far about this example and the conjecture? Okay, we mentioned that the conjecture 2 is related to other areas of mathematics. Here is a brief summary of how it's related. So first of all, it's related to the sum product conjecture raised by Erdős and Semeradi. The sum product conjecture says that if E is a finite set of R, then the maximum of the size of subset and the product set is greater than the number of points in A to the 2 minus epsilon for arbitrary small positive epsilon. Here, the sum set is defined as A1 plus A2 for any A1 and A2 in A, and so it's defined the product set. So this conjecture still remained unsolved, and there is some partial result. But one thing to notice is that here, the key point is that A is a finite subset of the real field. So if we replace R by the finite field, then this conjecture breaks down. So for example, if A equals to Fp inside the field Fp square, then we know that A plus A equals to A times A equals to A. So this whole conjecture breaks down. So this is a very discrete problem. Our conjecture 2 about the distance set of half dimension is related to a discretized version of the sum product conjecture. That is, if A is a subset of the interval 1 to 2, so this 1 to 2 is just to make the product set make sense, and is like a half-dimensional set at resolution delta. Then the maximum of the delta covering number of A plus A and the delta covering number of A times A is greater than the delta covering number of A to the power 1 plus epsilon. So here I didn't give a rigorous statement of the discretized sum product. So, but I hope you can kind of imagine that A is a set of delta intervals inside the interval 1 to 2 that arrange in a half-dimensional way, and then we calculate its sum set and to count how many delta intervals are there in the sum set, and also how many delta intervals are there in the product set. So this is epsilon above the trivial estimate. That is, A plus A should be like greater than the size of A. However, this epsilon is quite non-trivial to obtain. perhaps ideally we would want this to be a to the delta, so the delta covering number of a to the 2 minus epsilon as this conjecture, but it's unknown whether this is true. So by a theorem of Katz and Tau, they showed a few statements that are equivalent. I only list two. So the first statement is the precisely Bourquin's discretized sum product theorem is equivalent to the statement that if E is a one-dimensional subset in R2, then the Hausdorff dimension of the distance set of E is greater than 1/2 plus epsilon. So I must say that this theorem is raised a few conjectures and says that they are equivalent. And after that, Bourquin proved the discretized sum product conjecture. And that's why we have this theorem. So this theorem is a combination of these two results. Also, I want to point out that the best known bound for the Kakeya conjecture in R3 by Katz and Zhao is obtained. One ingredient in their result is the Bourquin's discretized. It's closely related to Bourquin's discretized sum product theorem. So this theorem is also related to the Kakeya conjecture in R3. So the bound they proved is that the dimension of the Kakeya set is greater than 5/2 plus epsilon, and the two epsilons, and the two epsilons, they are related. Now, so yeah, I wanted to talk about our main result. So the first result joined with Shmerkin is that we show that if E is a Borel subset of R2, and then the Hausdorff dimension of E is equals to U, that is smaller or equal to 1, then we show an explicit lower bound about the Hausdorff dimension of the distance set of E. So this, even though this is given by a somewhat complicated algebraic function, but I feel like it's kind of the artifact of our method. It does not really say that this should be the result. So maybe to give us a sense of what's the size of phi u, I think phi 1 is like 0.618 is like the golden ratio. And we also showed that if E is kind of special in the sense that the packing dimension of E equals to the Hausdorff dimension of E, then the Hausdorff dimension of the distance set is greater or equal than the Hausdorff dimension of E. So this is kind of the best we can hope for. Although this still remains like a partial result towards, say, the Hausdorff dimension of the distance set is greater or equal than U. It's worth mentioning some of the prior results. That's one important result is by Thomas opponent in 2016. It says that if E is a compact AD regular subset of R2, and the Hausdorff dimension of E is greater or equal than 1, then the packing dimension of the distance set equals to 1. here in this important paper, Thomas introduced the idea of decomposing a fractal set into different scales and then use entropy to merge all the scales together. And this idea we will see later. And then Kalati and Shmerkin used some of these ideas and combined with some new ideas. They show that if E is a Borel subset of R2 with Hausdorff dimension strictly greater than 1, then the Hausdorff dimension of the distance set is greater than 2/3. Here I highlighted the AD regular and the condition that the Hausdorff dimension of E is greater than 1, because those set, and also this condition, because only under this condition, we know that for a typical E, X in E, the radial projection pi x E defined as the following has Hausdorff dimension 1. But this is a very strong condition, and for general set, we don't know. And later we will see that what we know before. So all of those prior results have one common theme, that is the radial projection image has full Hausdorff dimension. And later we will see how this property come into play. So this is our first result. And then our second result is like a higher dimensional version that says that if the Hausdorff dimension of E is greater than D/2, then the Hausdorff dimension of the distance set is greater than 1/2. Sorry, here I made this is not true. Then the dimension here so then the dimension, I will specify which dimension is later. The dimension of the distance set is greater or equal to 1/2 plus CD. CD is a constant, an explicit constant given by some formula that's not quite important. So here, I think when D equals to 3, this is still Hausdorff dimension. But when D is greater or equal to 4, then we only have lower Minkowski dimension. And the second result, the second part of this result is if the packing dimension of E equals to the Hausdorff dimension of E, then the distance set has Hausdorff dimension 1. And also this is like the best we can hope for. And so the prior result in this topic is due to Pablo Shmerkin in 2020, saying that if in dimension 3, if E is greater than half dimension, like if the Hausdorff dimension of E is greater or equal to 3/2, then the Hausdorff dimension of the distance set is greater than 1/2 plus epsilon. And epsilon is a positive small constant. Again, this epsilon is related to the epsilon that we have discussed so far. But here we have, in dimension 3, we have an explicit gain. So those are all the two results that we are going to talk about today. Are there any questions about the statement? Okay, so Thomas Opponen introduced the idea of relating distance problem to projections. So here is how it's related. Assume that, let's say, Q is a box of size side length rho to the 1/2. And then, so X is a point in Q. And Y1 and Y2, they are distinct points that's far apart from Q. Let's say the distance between them is about 1. Then, for example, when we want to calculate the number of distinct distances up to scale rho from Y1 to E intersect Q. So let's say those points are E intersect Q. Then we see that we do some kind of projection that is orthogonal to the segment, to the vector from X to Y1. So this pink points, those pink strips are the level sets of the distance map defined by delta yx equals to the distance between x and y. So here we have 1, 2, 3, 4, 5 points, but we can see that the number of distances up to scale rho is 4 in this very special picture. And then for y2, we do we kind of do the orthogonal projection along the direction that's orthogonal to the vector from x to y2. So this is orthogonal. And then in this picture, we have 5 points, and the number of distinct distances is 3. So, but it's important that this Q has side length smaller than rho to the 1/2. And here we only care about distances up to error rho. Now this picture is how distance map is related to orthogonal projection. Then another thing we need to know that now we have related to orthogonal projection, but there is no guarantee that the orthogonal projection image is large unless we have a lot of directions. So this is how the radial projection come into play. So imagine we know that at this point x, there are a lot of y's in different direction. In other words, if we know that pi x e, maybe let's say e minus some neighborhood of q is large. So that's the radial projection is large. If we know that radial projection is large, then we know that we have a lot of directions. And then later we will see that we have some theorem that will guarantee we have a big orthogonal projection. And then we use some of the entropy language to merge the information at these different scales. That's how we obtain our result about the size of the distances. So I feel like this picture illustrates our main scheme of proof. So I will pause here and see if there are any questions. Okay. So So here, this slide is about different orthogonal projections results we have. That shows that if the number of directions is, the direction set is large, then we can always find a direction such that the orthogonal projection image is large. So orthogonal projection is defined as theta is a vector, then p theta is a linear map between R2 and R defined by X to theta dot X. So we have the classical Mass-Jones projection theorem says that if E is a Borel set, then for almost all vectors theta, the Hausdorff dimension of the orthogonal projection image along theta is equals to the minimum of the Hausdorff dimension of E and 1. Then here we ask for almost all directions. So imagine we have a limited set of directions we can choose. So that's the Kaufman's projection theorem, which says that if lambda is a subset of S1, then there exists theta inside lambda such that the orthogonal projection image has dimension equal to the minimum of the Hausdorff dimension of E and the Hausdorff dimension of the direction set. So another question is raised is that what if the set of directions is so sparse and it's so small? What can we do? So this is Bourquin's projection theorem, which says that as long as the Hausdorff dimension of the distance, the direction set is positive, then there exists such a direction in our set, such that the orthogonal projection image has dimension greater than 1/2 of the Hausdorff dimension of our set, plus some epsilon. But this epsilon is a very small implicit constant depending on the dimension of our set and the dimension of the direction set. So here this epsilon is very important because without this epsilon, this bound is easy by some transversality theorem. And this epsilon makes a whole lot of difference. And it's actually, again, related to all the epsilons we have discussed so far. And actually, this Bourquin's projection theorem is like an extension of his discretized sum product theorem. So he first proved the discretized sum product theorem, and then prove a more flexible version that is the projection theorem. And also because of this epsilon, going back to the sum product theorem, we know that the real field R does not contain a half-dimensional subring. So now let's talk about radial projections. The radial projection is defined as if Y is a point in RD, then pi Y is a map from RD except Y to SD minus 1 given by X and then the unit vector in the direction of from X to Y. And the both radial projection results are due to Thomas' opponent. The first one is if E is a Borel subset of RD and the Hausdorff dimension of E is greater than D minus 1, then there exists Y in E such that the Hausdorff dimension of the radial projection image equals to 1. Sorry, this shouldn't be 1. Equals to D minus 1. I must say that Thomas proved a much stronger result. So this is just for for the sake of presentation, I state a weaker and hopefully clear version of it, like a simpler version of it. And then the second theorem is, well, if we don't know, so if our set E has Hausdorff dimension smaller, what can we do? So the second theorem is that if E is a subset of R2 and it's not containing any line, otherwise the radial projection is trivial, then there exists Y in E such that the Hausdorff dimension of the radial projection image from Y is greater than 1/2 of the dimension of E. And this was later improved by Liu and Shen to 1/2 of dimension of E plus epsilon. And of course, as you might guess, this epsilon uses Bourquin's projection theorem. So back to our first theorem with Shmerkin. For the sets that we care about, this is the only, this part is the only radial projection theorem that we knew. And that's much weaker than, say, 1. So in other words, to improve our distance set result, we need to some kind of improve this theorem. Okay. So we have discussed different kind of maps. For example, the radial projection map, the distance map, taking a distance from X to Y. And all those maps have a common thing, that is, they are nonlinear projections. And so Pablo Shmerkin has this wonderful result about extending Bourquin's projection theorem to nonlinear projections. So let Fy be a family of C2 maps without singular points. So we should really think of Fy as the nonlinear projections we have studied, that is the radial projection or the distance map. And for each x, if we define theta xy as something related to the gradient of Fyx, then if we know that for any, so we have a set E, and for any x in E, the Hausdorff dimension of theta x, lambda is the parameter set, is greater than beta, that's some constant, some positive number. Then there exists Y in lambda such that the Hausdorff dimension of Fye, so that is E under this nonlinear map parameterized by Y, has dimension greater than 1/2 of the dimension of E plus epsilon, while epsilon positive is implicit and small depending on beta and the Hausdorff dimension for E. So I know this when we first see it, it seems the condition is a little complicated. But when we think if lambda is a subset of the unit circle, and then Fy is the orthogonal projection parameters by Y, so Y is a point, is a vector, then this map, theta xy, is identity. Is really identity. And then the whole theorem is back again to Bourquin's projection theorem. Also, I want to point out that Shmerkin's proof uses Bourquin's theorem as a black box. Maybe And then at the beginning, when we discussed the relation between distance set and the orthogonal projections, we have something like this is x, and then y1, y2, y3. So we want a lot of directions from x to other points. And I want to say that this condition acts more the same as what we have seen before. In other words, we need a lot of directions. And that's where this condition comes from. Are there any questions about the statement? Okay. If not, then I will use one slide to illustrate the main idea in our proof of our first theorem. That is the self-improving idea in R2. So before that, we still need to see another theorem by opponent Shmerkin. That is an absolute improvement over the Kaufman's projection theorem we have seen. So if E is a subset of R2 and lambda is a subset of the unit circle, a set of directions, they are Borel sets. And then the dimension of lambda is smaller than the dimension of E. Then there exists theta, a direction, such that the orthogonal projection image has dimension greater than dimension of the direction set plus epsilon, where epsilon is a small implicit positive constant depending only on the dimension of lambda and the dimension of E. So this part is the original Kaufman's projection theorem. And then the epsilon improvement, as you might be able to guess, also uses Fourier projection theorem. Then the main idea of our proof is to use this improved Kaufman's theorem as a starting point and to make it self-improving. So here is the picture. So this is again back to the picture we have studied. So we have a box cube of side length rho to the 1/2, and x is a point in cube, and y is another point that's sufficiently far away from cube. It has distance about 1. Then we studied the radial projection. As before, we said that we really want the radial projection to be large in order to apply good orthogonal projection theorems to obtain good distance set results. So to study the radial projection, here are the level sets of pi y. So that you can see that all the points in this line will have the same radial projection image. And if we calculate them, maybe here I shouldn't say equal, but parallel. So if we calculate this vector that is given by the condition here, it's parallel to pi xy. So in other words, if we know that pi xe has certain dimension, then the radial projection image will have a slightly larger dimension. So we apply improved Kaufman's theorem in the linear approximation of pi y. So here, by linear approximation, I really mean that we have a box of side length rho to the 1/2, and we only care about things up to scale rho. And this is the linear approximation. And it says that the dimension here. So here I'm being a little vague. This is not really dimension because it means up to scale rho. And for pi y of E intersect Q. So we have some points here, and then the radial projection image will be the levels that will be the produced point is greater than the Hausdorff dimension of pi xe, another radial projection image from X, plus epsilon. And this plus epsilon is precisely this epsilon. So here we can kind of see a loop of the reasoning. So if something is greater than moduli itself plus epsilon. So all those X and Y, they are points in E. And then so we can iterate. And this epsilon goes to 0 when the dimension of E intersect Q is approximately the same as the dimension of pi xe. So we'll certainly stop at 1, but we might stop before that. And this is like the rough main idea of our first theorem. So something I didn't say is that E intersect Q might not look like a set of the same dimension as E. So that's where when E has about the same packing dimension and Hausdorff dimension, we can morally think that E intersect Q has the same size as E. And so that this iteration will go smoother, like will work better. But if E is a general set, then we have to decompose E into different scales. And we use some combinatorial argument to optimize the gain we have. And that's where we have this funny looking function, theta phi u, and the golden ratio. But nevertheless, so this is the main kind of algorithm that we can iterate the epsilon gain to an explicit gain and even an optimal gain for special sets. I have 2 minutes left. I still want to say something about dimension reduction idea in higher dimension. And this idea was like kind of introduced in our joint paper with Yosevich, O, and John. And it looks simple, but to make it work, it requires a lot of technical justification. So here is some kind of idea in R3. That is, if E is a set of Hausdorff dimension 3 halves, then by some classical projection theorem, I think we found the theorem in a book of Kaufman and Matila, says that there exists a 2-dimensional subspace V such that we project E to V, it has the same dimension because E has dimension smaller than 2. So it has the same dimension. And we study the radial projection of this set, PVE. Now, by opponent's first radial projection theorem, we know that there exists a Y such that the radial projection will have dimension 1. That means we have a lot of directions from Y. And then we lift up, so that's like X is an actual point in E, but we know that this implies that if X in E and PVX equals to Y, then pi xe is greater than then the radial projection from X has dimension greater or equal than 1. So this step is simple, but we can actually hope for better because on each of those slices, we might have more points. So this will we hopefully can plus something here. And this is indeed what we are going to do. So by a slicing theorem, also classical, but I won't state it here, for a typical W, also a two-space, a two-plane that's orthogonal to V through Y. So there are many of those two planes. There, for a typical two-plane, the dimension of E intersect W is the dimension of E minus 1. In this case, that is 1/2. So we have, for X, we have a 1/2 dimensional set on this two plane. And then if we could apply opponent's radial projection theorem too, we know that the radial projection image on this slice has dimension 1/2 of 1/2. And if this really works, then the radial projection image has dimension that is better than 1. But this doesn't work as it is because this slice might be contained in a line, and then we need to rule this out. And we were able to use opponent Shmerkin's higher dimensional nonlinear Fourier projection theorem to rule this out. But this is not quite satisfactory. So that's why our result is around half dimension instead of all dimensions. I will stop here. I'm over time, sorry.